In this presentation, we will talk about the residual stress in AISI-316L and AISI-18Ni300 steels produced by selective laser melting. This study was developed at the University of Coimbra, where the residual stress analyses were performed by X-ray diffraction, in collaboration with the Faculty of Engineering of the University of Porto and INEGI, the Institute of Science and Innovation in Mechanical and Industrial Engineering, Portugal. The study was done by Maria José Marques, António Castanhola Batista, João Paulo Nobre, Filipe Fiorentino e Abílio Jesus. The additive manufacturing requires certain input heat levels to melt the powder material in repetitive cycles of melting and solidification. These process characteristics can result in defects such as porosity and unwanted residual stress, which may compromise the fatigue behavior or lead to distortion. The present project has as particular focus the comparison of residual stress generated in samples of different dimensions, produced by selective laser melting with two different materials, the AISI-316L and AISI-18Ni300 steel power. The obtained results will be used to validate the finite element model. Another presentation at this conference will show the finite element model under development. Here we can see the composition provided by the manufacturer of the metal powders used to produce the sample. The first one, the AISI-316L, is an austenitic stainless steel. And the second one, the AISI-18Ni300, is a maraging steel. The parameters of selective laser melting process used to produce the sample for each steel are indicated in the first table of this slide. The sample produced with AISI-316L powder will be called SS from stainless steel, while the sample produced with AISI-18Ni300 powder will be referenced with more from maraging. The sample were produced with two different dimensions for both steels, indicated in the second sample of this slide. We will refer the larger sample with the capital letter L and the smaller ones with the capital letter S, being the size of L sample equal to 120 times 17 times 17 millimeters, while the size of the S sample is 50 times 20 times 10 millimeter. Here we can see the surface appearance of the sample. The scan strategy and roughness are visible on the top surface. The residual stress analyses were performed by X-ray diffraction using a IXRD protodiffractometer. It was used manganese radiation for AISI-316L sample and chromium radiation for AISI-18Ni300 samples. On this slide, we can see the X-ray parameters used for the experimental acquisition and the sample referential. The residual stress were determined on the top surface, correspond to the XY surface, and on both lateral surfaces, the XZ surfaces, in two orthogonal direction. So, at lateral surfaces, the residual stresses were determined in the longitudinal direction, the X direction, and in the transversal direction, the Z direction. At the top surface, the residual stress was determined in the longitudinal direction corresponding to the X direction, and in the transversal direction, the Y direction. Concerning the experimental results, the phase identification on the sample were done by X-ray diffraction with Cooper radiation. As you can see here, in the AISI-316L sample, only the austenitic phase is present, while in the AISI-18Ni300 sample, the martensitic phase and also some residual austenite was detected. The quantification of residual austenite in AISI-18Ni300 samples were determined by X-ray diffraction with chromium radiation. The amount of residual austenite is 6% in both S and L sample on all lateral surfaces. However, at the top of the sample, the amount of the residual austenite is only 3%. of what was observed on the lateral surfaces. The roughness of top surfaces may be influencing these results. In these figures, we can see the microstructure of the sample for both steels obtained in a longitudinal section or perpendicular to the building direction, and in the transversal section, which is parallel to the building direction. As can be seen, the microstructure reveals how the deposition of the SLM was carried out, making it possible to distinguish the different springs of molten material in each pass of the laser and the layer-by-layer deposition. The Vickers microhardness were determined on the longitudinal and transverse sections. The results show the same microhardness for both sections, with the marching sample showing the highest value, 415 HV, due to the presence of the martensitic phase. Here we can see the residual stress results obtained at the top of sample and determined at different points along the red line, on sample of different size and for both type of steel. The residual stress on AISI 316L sample are tensile for both S and L samples. Residual stress are higher in the transverse direction and remained approximately constant across the AISI 316L sample from end to end. The residual stress in AISI 18Ni300 sample are also tensile at the top of the sample for both size S and L and for both longitudinal and transverse direction. However, residual stress are not constant from one end of the sample to the other, as on the austenitic sample. Here we can see the results of the residual stress obtained on the lateral surface at the S sample and for two types of steel, for several distances C from the build plate. The C distance from the build plate were 2, 5, 10 and 18 millimeters. The red lines in the figure are intended to help visualize and analyze the points. The residual stress are tensile on AISI 316L sample and compressive on AISI 18Ni300 sample for both X and Z direction. We can see also that the residual stress remain approximately constant across the AISI 316L sample from end to end. The most significant difference observed between the results of the two steels is the residual stress variation in Z direction, observed in the marrying steel. The intensity of the residual stress in this sample are higher near the build plate, where Z is equal to 2 mm, and decrease near the top of the sample, where Z is equal to 18 mm. Here we can see the results of the residual stress obtained on the lateral surface of L sample and for the two types of steels at different distance C from the build plate. See the red line in the figure to understand where are located and analyze the points. The Z distance from the build plate are 2, 7 and 15 millimeters. Observing this graphic, we see that the evolution of the residual stress in this L sample is similar to what was observed in the previous slide for the S sample. The residual stress remained tensile on AISI 316L sample, while the residual stress are compressive on AISI 18Ni300 sample for both X and Z direction. The intensity of compressive residual stress in the Z direction are higher near the build plate, where Z is equal to 2 mm, and decrease near the top of the sample, where Z is 15 mm. Now we are going to conclude this presentation, reporting the main conclusion of this work. On AISI 18Ni300 sample, the presence of residual austenite was detected and quantified by X-ray diffraction at lateral and top surfaces for both S and L sample. The results shown 6% of residual austenite at lateral surface and 3% at top surface in both S and L sample. A constant Vickers microhardness value of 415 HV was determined in both longitudinal and transversal cross section. Concerning the S and L AISI 316L sample, the X-ray diffraction show only the presence of austenitic phase in the samples. The Vickers microordnance test allowed to determine the value of about 300-315 HV in the longitudinal and transverse section for all S and L samples. All samples of both steels show the typical microstructure of the selective melting process. Residual stress at the top and at the lateral surface of both S and L AISI 316L specimen are always tensile and have a similar value regardless of sample size. The residual stress are greater in the transverse direction than in the longitudinal direction on all surfaces observed of AISI 316L samples. The residual stress remain constant from one end of the specimen to the other. Concerning the results obtained on AISI 18Ni300 steel samples, the residual stress are tensile only at the top surfaces. On the lateral surfaces, the residual stress on AISI 18Ni300 steel sample are compressive and are higher in absolute value near the build plate. It was also observed that residual stress value increased from one end of the sample to the other. We would like to thank FEDER and FCT for their financial support to this study. Thank you for your attention.